So in this episode, we will be discussing the Kubernetes object model in the beginning, and then we'll go on to other topics. Kubernetes objects are persistent entities in the Kubernetes system. Kubernetes uses these entities to represent the state of the cluster. Specifically, they can describe what containerized applications are running and on which node, the resources available to those applications, and the policies around how those applications behave, such as restart policies, upgrades, and fault tolerance. A Kubernetes object is a record of intent, which means once you create the object, the Kubernetes system will constantly work to ensure that the object exists. By creating an object, you are effectively telling the Kubernetes system what you want your cluster's workload to look like. This is your cluster's desired state. To work with Kubernetes objects, whether to create, modify, or delete them, you'll need to use the Kubernetes API. When you use the kubectl command line interface, for example, the CLI makes the necessary Kubernetes API calls for you. You can also use the Kubernetes API directly in your own programs using one of the client libraries which are supported by Kubernetes. Python and Java are one of the few languages which are supported. Kubernetes has a very rich object model representing different persistent entities in the Kubernetes cluster. Those entities describe what containerized applications we are running on which node, application resource consumption, and different policies attached to applications like restart, upgrade policies, fault tolerance, etc. This is what we've mentioned before already. With each object, we declare our intent in the spec section. The Kubernetes system manages the status section for the objects, where it records the actual state of the object. At any given point of time, the Kubernetes control plane tries to match the object's actual state to the object's desired state. Examples of Kubernetes objects are pods, ReplicaSets, deployments, namespaces, etc. We'll be discussing more about these objects in this episode. When we create an object in Kubernetes, we must provide the object specification that describes its desired state, as well as some basic information about the object, such as name. When you use the Kubernetes API to create the object, that API request must include that information as JSON in the request body. Most often, we provide the information to kubectl in the YAML file. kubectl proceeds to convert the information to JSON when making the API request. In the specification file, that is the YAML file that we provide to Kubernetes, the API version field is the first required field. It specifies the API endpoint on the API server which we want to connect to. It must match an existing version for the object type defined. The second required field is kind. This specifies the object type. It could be the deployment, pod, replica set, namespace, service, etc. The third required field is metadata. This holds the object's basic information such as name, labels, namespaces, etc. Once the object is created, Kubernetes system attaches the status field to the object. Now, let's discuss pods. A pod is the smallest and simplest deployable Kubernetes object. It is the unit of deployment in Kubernetes which represents a single instance of the application. A pod is a logical collection of one or more containers which are scheduled together on the same host with the pod, share the same network namespace, have access to mount the same external storage, that is the volumes. Pods are ephemeral in nature and they don't have the capability to self-heal by themselves. That's the reason they're used with controllers which handle pod replication, fault tolerance, self-healing, etc. Example of such controllers are deployments, ReplicaSets, replication controllers, etc. We attach a nested pods specification to a controller object using the pod template. Usually, we don't need to create pods directly, even singleton pods. Instead, we create them using workload resources such as deployment or jobs. If your pods needs to track state, we generally consider StatefulSets resource. Pods in Kubernetes cluster are used in two main ways. The first one, pods that run a single container. The one container per pod model is the most common Kubernetes use case. In this case, you can think of a pod as the wrapper around a single container. Kubernetes manages pods rather than managing the containers directly. And the second case is pods that run multiple containers that need to work together. A pod can encapsulate an application composed of multiple co-located, tightly coupled containers, which need to share resources. These co-located containers form a single cohesive unit of service. For example, one container serving data stored in a shared volume to the public, while a separate sidecar container refreshes or updates those files. The pod wraps these containers, storage resources, and an ephemeral network identity together as a single unit. When we specify the pod object in our YAML file, the API version that we need to specify in the case of pod is v1. Now let's discuss replication controllers. Although no longer a recommended method, a replication controller is a controller that ensures a specific number of replicas of a pod is running at any given time. If there are more pods than the desired count, a replication controller would terminate the extra pods, and if there are fewer pods, then the replication controller would create more pods to match the desired count. Generally, we don't deploy a pod independently, as it would not be able to restart itself if terminated in error. The recommended method is to use some type of replication controller to create and manage pods. The default controller is a deployment which configures a replica set to manage pods lifecycle. Now let's see what replica sets are. A replica set is the next generation replication controller. Replica sets support both equality and set-based selectors, whereas replication controllers only support equality-based selectors. Currently, this is the only difference. With the help of replica set, we can scale the number of pods running a specific container application. Scaling can be accomplished manually or through the use of an autoscaler. Replica sets can be used independently as pod controllers, but they only offer a limited set of features. A set of complementary features are provided by deployments, the recommended controllers for the orchestration of pods. Deployments manage the creation, deletion, and updates of pods. A deployment automatically creates a replica set, which then creates a pod. There's no need to manage replica sets and pods separately. The deployment will manage them on your behalf. So we've seen this word deployment so many times already. Now let's just talk about it a little bit. Deployment objects provide declarative updates to pods and replica sets. The deployment controller is part of the master node's controller manager, and it ensures that the current state always matches the desired state. It allows for seamless application updates and downgrades through rollouts and rollbacks. And it directly manages its replica sets for application scaling. A rolling update is triggered when we update the pod's template for deployment. Operations like scaling or labeling the deployment do not trigger a rolling update. Therefore, do not change the revision number. Then comes namespace. If multiple users and teams use the same Kubernetes cluster, we can partition the cluster into virtual subclusters using namespaces. The names of the resources or objects created inside a namespace are unique, but not across namespaces in a cluster. Generally, Kubernetes creates 4 default namespaces. They are kube system, kube public, kube node lease, and default. The kube system namespace contains the objects created by the Kubernetes system, mostly the control plane agents. The default namespace contains the object and resources created by administrators and developers. By default, we connect to the default namespace. Kube public is a special namespace which is unsecured and readable by anyone. It's used for special purpose such as exposing public information about the cluster. Good practice, however, is to create more namespaces to virtualize the cluster for users and developer teams. With resource quotas, we can divide the cluster resources within namespaces. Now let's discuss jobs and cron jobs. A job creates one or more pods to perform a given task. The job object takes the responsibility of pod failures. It makes sure that the given task is completed successfully. Once the task is complete, all the pods have terminated automatically. Job configuration options include parallelism to set the number of pods allowed to run in parallel, completions to set the number of expected completions, active deadline seconds to set duration of the job, back-off limit to set the number of retries before job is marked as failed, TTL seconds after finished to delay the cleanup of the finished job, starting deadline seconds to set the deadline to start a job if scheduled time was missed, and concurrency policy to allow or forbid concurrent jobs or to release old jobs with new ones. Now, let's discuss some of the advanced objects. One of them is DaemonSets. In cases when we need to collect monitoring data from all nodes or to run storage daemon on all nodes, then we need a specific type of pod running on all nodes at all times. A daemon set ensures that all or some of the nodes run a copy of a pod. Daemon set is the object that allows us to do just that. It's a critical controller API resource for multi-node Kubernetes cluster. The kube proxy agent running as pod on every single node in the cluster is managed by daemon set. Whenever a node is added to the cluster, a pod from a given daemon set is automatically created on it. Although it ensures an automated process, daemon set pods are placed on pods by cluster's default scheduler. When the node dies or it's removed from the cluster, the respective pods are garbage collected. If a daemon set is deleted, all pods it's created are deleted as well. A newer feature of daemon set resource allows for its pods to be scheduled only on specific nodes by configuring node selectors and node affinity rules. Similar to deployment resources, daemon set supports rolling updates and rollbacks. Some typical uses of a daemon set are running a cluster storage daemon on every node, running a logs collection daemon on every node, and finally running a node monitoring daemon on every node. That is, when we want a particular kind of pod to run on every node of the cluster, we use daemon sets. And the last Kubernetes object that we'll be discussing in this episode is StatefulSets. StatefulSet is the workload API object used to manage stateful applications. StatefulSets manage the deployment and scaling of set of pods and provides guarantees about the ordering and uniqueness of these pods. Like a deployment, a stateful set manages pods that are based on an identical container spec. Unlike a deployment, however, stateful set maintains sticky identity for each of their pods. These pods are created from the same spec but are not interchangeable. Each has a persistent identifier that it maintains across any rescheduling. If you want to use storage volumes to provide persistence for your workload, you can use a stateful set as part of the solution. Although individual pods in a stateful set are susceptible to failure, the persistent pod identifiers make it easier to match existing volumes to the new pods that replace any that have failed. Stateful sets are valuable for applications that require stable, unique network identifiers, stable, persistent storage, ordered, graceful deployment and scaling, or ordered, automated rolling updates. Stable in this case is synonymous with persistence across pod rescheduling. If an application doesn't require any stable identifiers or ordered deployment, you should deploy your application using a workload object that provides a set of stateless replicas. Deployment or replica set may be better suited to your stateless needs. Stateful set pods have a unique identity that's comprised of an ordinal, a stable network identity, and a stable storage. This identity sticks to the pod regardless of which node it's scheduled or rescheduled on. For a stateful set with n replicas, each pod in the stateful set will be assigned an integer ordinal from 0 through n-1. That's unique over the set. So this concludes the Kubernetes object model, and we have also discussed some of the objects in Kubernetes. There are few other objects in Kubernetes, but those are, beyond the scope of this podcast.
If you like this episode, please consider following us wherever you hear your podcasts.